Hello everyone, my name is Kanokwan and today I will present my work entitled Iterative Approaches to Variational and Fixed Point Problems with Application. The presentation is organized into four main parts. First, I will give a general introduction to iterative methods, variational inclusion problems, and fixed point problems. Then I will state the objective of work, present the main algorithm, and convert result. And finally, discard the numerical application. Before going to the technical part, I will start with background and motivation. This part explains why these problems are important and why a new iterative method is useful. Iterative methods approximating solution of nonlinear problems step by step. Starting from one initial point, they generate a convergence sequence. The first related class is fixed point problems. The second class is relational inclusion problems. The third class is minimization problems. And the fourth class is monotone inclusion problems. And these classes are connector iterative splitting technique. And we interesting in variational inclusions problem. Variational inclusion can be viewed find a zero of an operator. This is classes an important mathematical problem. It appears normally in optimization, image processing, signal recovery, and machine learning. Therefore, especially algorithms for includes are highly useful. And this motivates the algorithm developed in this work. And formally, we seek x star such that 0 belongs to T of x star. Here, the operator T is decomposed into A plus B. A is a single value, and while B is a set value. And thus, the target problem is 0 into A plus B at x star. The solution set is denoted by A plus B inward of 0. This splitting from arrows forward, backward type algorithms. And the classical approach, the forward backward splitting method, is developed by Lyon, Mercier, and Pasty. However, it requires the operator A to be cohesive. And then things is weak this assumption by modifying forward backward method. In thing method, I only need to be monotone. The step side can be fixed or chosen like such. So the cohesive assumption is removed, but it needs an extra forward evolution of A. Malinsky and Tam then proposed the forward Leifik backward method, or the Leifik term used to collect the previous operator value. And this method also avoids the cohesive assumption. And point and core order later consider a modified version. They introduce a variable step size update every iteration. And the step size is computed by a self-adaptive formula. This reduce depend on Lipschitz constant. And next, a fixed point problems are for x star equal to t of x star. The set of such point is called fixed of G. Many algorithms can be interpreted as fixed point iteration. This is example in the Picard iteration. Is repeatedly applying G into current iteration, but Picard iteration may fail for non-extensive mappings. Consider G of x equal to 1 minus x. Its unique fixed point is 1/2. Starting from 0.2, the sequence alternates between 0.2 and 0.8. Therefore, the sequence accurate and thus not convergent. This motivates more stable iterative scheme. One important scheme is main iteration. It evaluates the current point with image under G. With constant relaxation, it becomes Krasnowski iterations. When the relaxation is 1, it reduced to Picard iteration. Thus, main iterations generalize the Picard method. For strong conversion, hyper iteration use an issue point and ensure guide the sequence to a select solution. Another related method is viscosity approximation. This technique improves convergent behavior. Ishikawa iteration handles Lipschitz with pseudo-conjective mappings using two-step. Now we interesting is common solution problem. We combine inclusion and fixed point requirement. We seek a common point satisfying the both conditions. First is must solve variational inclusion, and second is must belong to fixed point set of G. This common solution is denoted by P, and this is lemma for sure link the common solution. In the lemma 1.1, it links 0 of B with the fixed point of its resolvent. The resolvent is J either B equal I plus either B inward. So, solving an inclusion can become to a fixed point problem. And lemma 1.2 gives same idea for A plus B is define the forward backward operator using A and resolvent of B. Therefore, the zero of A plus B is corresponding to a fixed point. And this is Lillard method. Frequency, Kanokwan, Kratuloek introduce an iterative method does not require concurrency of B. This is combined initial Ishikawa step and forward backward forward collection. And I now move to the objective of this work. We develop an initial forward reflex backward method for a common problem. The method works without assumption concurrency. It used Ishikawa collection for the fixed point constant. And it needs only one resolvent and one forward evaluation per iteration. And then we prove the conversion and test its classification. And this relate method and next I state the main result. The assumption C1 say that solution set phi is not non-empty. Assumption C2 is say A is a maximum monotone and B is a monotone Lipschitz. And assumption C3 says G is a pseudo-contractive and Lipschitz continuous. And algorithm 1 is setting IFREBSMIF. Algorithm 1 is combined initial Ishikawa collection and reflect backward splitting. And the main result under this condition, the generalized sequence convert weakly to a point in phi. And now I present the application. We apply the method to binary medical classification. The two datasets of heart disease and weight sensor. The model is based on extreme learning machine. The goal is to demonstrate particle performance. In ELM, The output weight matrix defines Tx equal to C. To reduce overfitting, we use an L1 localized model. Its optimality condition become monotone inclusion. And the heart disease dataset has 303 instant and 13 feature. And the B sensor dataset has 569 instant and 30 features. Both are binary classification problem with 10 for cross validation. And we compare log loss and equivalency with RIA IF algorithm proposed by Kanokwan 2024 we or in short RIA algorithm. For the board dataset, log loss decreases with iterations. Accuracy increases and becomes stable. The close taining or testing curve indicate good generalization. And our algorithm is achieve lower taining and testing log loss than RIA algorithm. This showed the better probability-based classification performance. And for accuracy, our algorithm is also perform better on the board datasets. The heart disease testing's accuracy improved from 0.68 to 0.83. And the breath sensor testing accuracy improved from 0.78 to 0.97. This table summarization the training and tracing accuracy. Overall, our algorithm is outperforms RIA algorithm in both metrics. In caution, we propose an anti-shell forward refit backward speeding method, and the method handle non-conclusive operator by refit forward strategy. It is essential one left win and one forward evaluation per iteration. And we estimate weak convergence under suitable assumptions. And numerical results so confirm effectiveness for medical classification. Thank you for your attention.